Section 1.1 in our first video here is going to start by just kind of giving us an overview of some of the major areas of study that we're going to embark on this semester in calculus. Kind of every section of notes, the objectives will be listed at the beginning of every section. I may or may not always read those at the beginning of every video because we'll be starting different videos at different points of different sections. But for this first one, let's just start looking at this first question about the rate of change of a function at a specified point. So this will kind of drive a lot of what we talk about in the first part of the course, where we really focus on differential calculus. So first, let's just kind of think of a linear function. A linear function has the defining characteristic that between any 2 points on that line, it has a constant rate of change. So its rise over run is maybe here I go up 2 and to the right 4. So the rise over run maybe is 2 over 4, which would reduce to 1/2. Maybe I look at the rate of change between these 2 points, and maybe here, maybe that rise over run is just up 1 and over 2, okay? But of course that gives me the exact same slope. So this is the defining characteristic of a line. The pitch, the steepness, it's the same throughout the whole function. Any other function, all nonlinear functions, do not have this characteristic. So think about, maybe your familiar function, the parabola. The parabola starts off with a decreasing, so some types of, negative rates of change, and then later it's increasing, so positive rates of change. And if you were to kind of picture yourself traveling along this function, so suppose you're walking along this function going from left to right. Initially it's really steep, and then as you get closer to the origin, it kind of becomes a little bit less steep, sort of flattens out a bit. And then as you make the turn, now you've went from negative, a decreasing slope, to a positive or an increasing slope. Again, it starts off, as we're going from kind of left to right here, it starts off not very steep, but then if you're walking up this function, it continues to get more and more steep. So the idea is, if I wanted to know, let's say, well, what is the steepness right at some specified point? If that's what we were interested in, how we're going to visualize that is going to be with the line that we can draw that just touches only the function at that specified point. And even looking at like my little chicken scratch graph here, you can kind of see that the line and the function itself are extremely close to one another when you're right near and very close to that point. So this tangent line, this line that touches at just that specified point, that's what we're going to use to graphically display or represent the rate of change at a specified point. So when we start off looking at this first function here, whatever that function might be, if my point of tangency interest here is at x equals a, then the goal here is really to find what the slope of this tangent line would be. So the goal would be to find the slope of this tangent line. And so we're going to represent that as m for slope. So m for slope. And then we're just going to have a little subscript tan there for the tangent line. Okay, so the slope of the tangent line is going to be represented by this notation right here. Okay, so that becomes my goal, what I'm trying to find. All right, well, again, as we kind of go down to this next graph here, so again, we have the same goal here. So the goal is to try to come up with representation for the slope of that tangent line. Well, historically, when we've always talked about slope, it's always been, change in y over change in x. So I always needed 2 points on a line in order to find the slope of that line. So here's what let's say what we know is that we know we can find the slope of a line that goes through 2 points on the function. So we know we can find the slope of what we're going to call the secant line. So we can find the slope of a secant line, which is going to be the line, a line, that goes through that initial point of tangency interest down here, and then some other point on the function. So we're going to represent that with a little m for slope, and then SEC to represent the subscript there, to represent the slope of the secant line. So that is what we know how to do, right? I mean, we know how to find the slope of a secant line, or the line that goes through 2 points. We can just do good old change in y over change in x. So y2 minus y1 over x2 minus x1. Well, in this situation, if we do that with the point a, f of a, and then some other point on the function x, f of x, then we get the slope of this secant line as being f of x minus f of a over x minus a. But we might look at that and say, well, yeah, okay, I mean, I guess I can do that, but how much good is it doing me? How good is the approximation of that secant line for the tangent line? And I would say on my first graph I just did here, not so good. But what we can do is we can move the x's closer to that point of tangency interest. And that's what you're going to see on this next graph. So on this next graph, what we're showing here is that the x coordinate, the second point, let's say, on this function, this is where the x is going to be moving closer, like y goes so far out. Let's move that x closer to that point of tangency interest. And then what we want to really observe here is as the x is moving closer, so as the x moves closer to that original point A, that point of tangency interest, the point where we want the slope of the tangent line there. So as the x moves closer to that point A, what we're kind of just visually observing here is that the slope of the secant lines, the slope of these secant lines that we're seeing here, the slope of these secant lines are really getting closer and closer to that which we are trying to come up with a measurement for. They are approaching the slope of this tangent line. So this is the limiting concept. So what we are doing here is we are letting the x's approach A. And the notation that we're going to be using really just right away in this first section is going to be the limit as x approaches A. And so as x gets closer and closer to A, the slope of the secant line, which is what we see right here, the slope of the secant line is going to be approaching that slope of the tangent line. All right, so let's just look at a numerical example, just kind of one more example with this concept, because this is what we're really going to be working up to kind of in the first chapter or so. All right, so again on this one, I'm interested in finding the rate of change or the slope of the tangent line at 1, 1. So again, this is my goal right here, is the slope of the tangent line, the rate of change at 1, 1. And so once again, we're kind of seeing a similar graph as the last one we just did up there. And so what we want to just kind of observe here is that as the x's are approaching, as the x's get closer and closer really to 1. So down here, the point of tangency interest is at 1. And the line in blue is over here at 2. So that's the first x. And then that slope was 3. And then we go out from 1, we just go to 1.5. This is not necessarily drawn to scale. And so that slope, that's the green one, is 2.5. And then we go out to 1.25. And then that slope, that's the one we're seeing in red, that one's 2.25, and so on. So again, what we're seeing here is that the x, that kind of that second point, I guess you could say, is getting closer and closer, kind of moving closer and closer into that point of tangency. So as the x is approaching 1, what we want to observe is that the slope of those secant lines is really approaching the slope of the tangent line that we are interested in finding. So it's approaching the slope of that tangent line. And in this case, we actually have some numerical values that we can actually look at here. So in this situation, if we actually look at the values of those slopes, meaning the slopes of those secant lines, we can kind of look, and we're going from 3 to 2.5 to 2.25 to 2.1, and I think we can pretty reasonably say that a good guess for us at this point would be to say it looks like the slope of these secant lines is approaching. If I had to make my best guess for the slope of this tangent line, I would say it's probably 2. So this is the idea of, even though I can't yet, kind of prove this to you, this is really the graphical idea of what we're going to be developing. So that's kind of the first major branch of calculus we're going to be studying, and where the limit idea is going to come into play. Oops. All right, now another major branch of calculus that we're going to be working on later in this semester is going to be called integral calculus, where we're going to concern ourselves with trying to find areas under curves of arbitrarily shaped regions. And so I'll move through this part pretty quickly. Essentially, okay, I don't have a formula for the area under some arbitrarily shaped region, but what do I know how to do is find areas of rectangles. So if I divided that region up into 5, 10, 15 rectangles or so, look at these 4 pictures and notice how visually the error is becoming less and less as we use more and more rectangles. You can visually see the error in the first rectangle, or in the first picture with only 5 rectangles. Oh, this is, that's error right there because that's too much. It's an overestimate. And then over here in this region, oh, that's not good. I'm not getting enough. I'm supposed to be getting this area and I'm not getting it. So in these first couple of pictures, you can really see visually the error. But as we start to let our number of rectangles go to infinity, by the time we get to this last picture, and if you notice the actual areas of those rectangles is given, that's what's in blue here. But by the time we look at the last picture, it's very difficult to even see the error anymore. It kind of really just looks like it's shading what's really close to being the area under that curve. So again, on this one, what I want us to kind of from these pictures just to notice is I want you to observe that as, there's 2 different ways that we could say this. We could say as the number of rectangles, which we might refer to as the variable n, but I'll just leave it in words. So as the number of rectangles, which I left out my e, goes to infinity. So as I get more and more rectangles, or equivalently, I could say as the width of the rectangles is getting smaller and smaller and smaller. So in both of these pictures, those two are essentially equivalent statements, right? So I could either kind of phrase it as the number of rectangles goes to infinity, or I could say as the width of the rectangles is going to 0. So those are kind of saying the same thing. What we're kind of noticing here is that in that situation, the area of these rectangles is actually approaching the actual area under the curve. So it's approaching the actual area under the curve. And so these two ideas both rely on this limit idea. So let x approach a, let n go to infinity, let the width go to 0. Both of these really important fundamental processes that we're going to be studying this semester, both of these rely heavily on this concept of the limit. So both of these rely on something called the limit. And that is exactly where we are going to start our next video with. We're going to get into the meat of how we evaluate a limit.